Hello everyone, welcome back to the class real-time system. Okay, so far we have discussed about the introduction and general purpose computer and single chip microcontroller and microcomputer and processor related interfaces. I mean, it's not that specialized processor. So in specialized processor we have discussed about the two topics, the parallel computer and also digital signal processor. In parallel computer, we discussed about the four architecture: SISD, SIMD, MIMD, and MISD. So these are the four architecture. In diagram, in detail, we discussed about, right? So now we are going to talk about the process related interfaces. Okay, so in this process related interfaces, the instruments and then actuators, the connected to the processor or the plant that can take the wide range of forms. Okay, so in these operations, there are needed to convert the digital quantity in form of the bit pattern in a computer board. It's a physical quantity or to convert the physical quantities. See, actually, what is the thing is, here we are connecting the microcomputer, I mean the plant which is connected to the controlling operations. Okay, so now we need to control the whole industry. Okay, so that industry output, it may be an analog quantity or it may be an digital or it may be on the pulse or it may be on the other formats also. So now what is the thing is that process related interfaces is nothing but we are going to interface that kind of interfacing which is related to that, which is if it is on transferring the analog interfaces, we can connect digital interface, we connect and also we can connect the pulse interfaces. Like that, the many interfaces we can be connected. Okay, so that bit pattern, whatever the outputs which is produced from the plant, it may be on any kind of forms. Okay, so the devices can be allocated in one of the following categories. What are those things? It may be on digital quantity, it may be an analog quantity, it may be on pulse or pulse rates, or it may be a telemetry signal. So the digital quantity is nothing but the binary wall. It is an open or closed, or relay which is open or closed, or BCD output which is the VCD output or of the voltmeter. Okay, analog quantities are what? The thermocouples, strain gauges, and that gives the output which is measured in multivolts and amplified using the operational amplifier to the range of -10 to +10 volt. So these are the continuous variables and have to be both sampled and converted into the digital value, because we cannot process the analog signals, we cannot transfer the analog signals for the long distance. So that's why we need to convert the analog signals into the digital form. So for that we need a sampling and quantization operation. Okay, so and third signal is nothing but the pulses and then pulse rates. So the flow meter, and that provides the output in the form of the pulse trains and stepper motors, and the inputs are the pulses. And telemetry is nothing but remote applications. Okay, so you need remote outstations like on the electricity substations and then gas pressure reduction stations. So there is a usage of telemetry to control. So the data may be sent using the landline, or it may be on the radio, or it may be on the public telephone network with the data and sent serially in the ASIC format. Okay, now now we are going to discuss about there are four different interfaces. One is the digital signal interface, pulse interface, and analog interface, and also a real-time clock. So the first we are going to discuss about this, the digital signal interfaces. Here you can see here it is plant. Whatever the plant, the inputs which will be sent into the digital input register, and that is sent to the address decoder. Okay, so by using the address decoder, that whatever the data will be registered, that will be sent to the CPU. Okay, now what are the operations which is performing in this digital signal input interface we are going to talk about here. So we know that this is the simple diagram of the input interface of the digital signal, and it is assumed that the plant outputs are the logic signal which appears on line connected to the digital input register. Okay, which is connected to the input register. Now the transfer one word at a time to the computer, and then logic levels on the input lines will typically be 0 and +5 volts. So to read the line connected to the digital input register, the computer has to place the address of the register on address bus, and decoding circuitry it is required in the interface to select the digital input registers. And this is all about here the input interfaces of the digital signals. Okay, now similarly the same thing which is given here also. So here if you can see here, it is transfer the one word at a time of the computer. So normally the digital input signals will have a same number of input lines and the number of bits in the computer word, so which requires 0 to 5 volts. Okay, like this it is given. So here what apart from this, what it is given is to read the line connected to the digital input interface, the computer has to place the address on the address bus and then decoding circuitry to perform the address decoding. Okay, to select and enable the signals that may be required, the time comes from the computer control bus. When the both are available, the register enables its output gates. So the timing of the registers of information is governed by the CPU timing, the transfer which takes the 3 cycles, the T1, T2 and T3. So the address lines goes to change at the beginning of the address. So here you can see here the beginning of the address will be placed, and the data will be read. I mean it will check whether the read signal is on or not. If it is on, the data will be placed into the data line. Okay, so minimum it requires the three clock cycles. So the timing diagram of the simple read clock cycles which is given here. Okay, and so this is nothing but on the digital signal output interface. So what and all the operations of there is output interface we are going to talk about here. So if you see here, whatever the output register data, so after processing all the information, the informations need to be sent to the plant. So through the digital signal interfacing we are going to connect it here. So the same diagram, and then output registers are there. That output register will send to the plant, intimate to the plant. Your simple digital interface. So this is the diagram of the simple the output interface, where the digital output is simplest form of the output. It requires a register or latch which can be hold the data's output from the computer. So the output from the latch is to set the logic levels, typically 0 to plus 5 volts. Okay, generally it is on 0 to plus 5 volts. If these logic levels are not accurate to operate the actuators on the plant, then the some signal conversions which is necessary. So the digital input and then output interfaces that can be used to accept the BCD data from the instruments, as they are essentially the parallel digital input and also a output devices. Okay, so this is all about a digital signal interfacing. Okay, so to avoid the data of the register from changing when the data on the data bus changes, the output must be respond only when it is addressed or when it is enabled. So enable tells that the data is stable, latch should accept the data quickly, and the output of the latches and logic level, if not adequate, then the level conversions which is required, the relay can be used here to achieve the electrical isolations. Okay, so now the next we are going to talk about here the pulse interface. So similarly for the plant we are going to interface with the pulse. So if it is the pulse interfacing which is connected to the plant, how it operates, what are the block diagrams are there, what are the functions which is performing that interface, the pulse interface. Okay, so this is the simplest form of the pulse interface, is consisting of a counter. It's consisting of the counter. So here you can see this pulse counter to the line from the plant, and this is the figure which shows both the input and output interfaces. So in earlier the digital interfacing we have talked about the two different diagrams, one is the input interface and another one is the output interface, but here in the single diagram we are going to connect, I mean the two interfaces are connected in a single interface. Okay, so this is the simple form of the pulse input interface. It is consisting of a counter connected to the line from the plant, and then the counter is reset whenever the program counter are read by the computer. Okay, so whenever the program counter and the fixed length of the time, and then counter reads by the computer. So here you can see here the pulse which is connected to the so the pulse counters are there. The pulse counter it will be keep on counting. The counter is nothing but it is keep on counting. At the fine time it need to be reset to 0. When it will be reset to 0, depending on the program counter. So the program counter used to count the counter value, increment the counter value. When it is reset, the counter value must be 0. Okay. And the measurements of the length of the time for which the count proceeds, that can be carried out either by the logic circuit or the counter interface or by the computer. So the pulse output can be taken in variety of forms. One is the series of pulse of the fixed duration, and second one is the single pulse of variable length. Okay, and the third one is the pulse width modulation, a series of pulse of different width sent at the fixed frequency. Actually, in the first one, the series of the pulse of the fixed duration, the computer turns a pulse generator as on or off, or loads the register with a number of pulses to be transmitted, and the pulse output is sent to the processor and used to decrement the register content. Okay. When the register reaches to 0, the pulse output is turned off. Example, to control the movement of the stepping motors. Okay. So when it come to this second type is nothing but a single pulse of variable length. So the computer rises or lowers a logic line and thus sends the variable length pulse to the plant, or that loads the register with a number of specifying the length of the pulse required and the interface logic which is used to generate the pulse. And when you come to this third one, the pulse width modulation, the pulse width modulation which is called PWM. So that are the special purpose interface chips used to generate the pulses. Okay. Like this how the pulse will be generated, and it will be connected to the plant. So whatever the operations which is performing, it is based on the pulse. Okay. So this is all about your pulse interfaces. And the next one is, so the next is analog interface. In analog interfaces also there are two diagrams, input side and output side, which is represented separately. So we know that the analog interface which is connected to the plant, that means whatever the signal which is receiving from the plant is nothing but an analog. So that kind of analog signals need to be converted into the digital form. So to perform that, we need a sampling and hold circuit. Okay. So the sampling and hold circuit which is required. So now the sampling and hold circuit, if we use the multiple quantities we are measuring from the plant. So if we use the different the sampling and hold circuit, I mean the analog to digital converter, if we are using, that is analog sampling and quantization is nothing but an analog to digital conversion. If we use a different circuit for different quantity of the data which is measuring from the plant, it is not at all worthful. I mean the cost of the plant interfacing will be more. So that's why we are going for the single analog to digital converter, and the data which is taking from the plant can be sent to the multiplexer. So the multiplexer output is nothing but a single output from the multiple inputs. So from the multiple input, any one of the output will be selected based on the priority or whatever it is, depending on the control signals. Okay, so that will be sent to the analog to the digital conversion, and the analog to digital conversion will be converted into the analog to the digital, and the digital will be sent to the different part of the circuits. Okay, so this is what given here, the conversions of analog measurements to the digital measurement, which involves sampling and quantization. So many analog to digital converter, which includes sample and hold circuits and the input to the device, and the computer which issues the start and sample signal, typically a short pulse, and in the response the ADC switches the sample and hold into the sample for the short period, and after which quantization process commences. So on completions of ADC rises, the ready or complete line which is either pulled by the computer or used to raise the interrupt. So the use of the separate analog to digital conversions for the multiple input is expensive, hence it is multiplexed. So it proves to be a more complex than the single channel devices. That selections of the channel at appropriate time should be arranged in sequence or random sequences. Okay, so that is nothing but an input interface side. Now it is an output interface side. So here you can see this, the different digital to analog conversions are used. Now again the informations need to be sent to the plant, whether it is, if there is any error signals are there, if there is any mismatches need to be corrected, or if it is everything is okay. So whatever it is need to be sent to the plant. So again it is converted into the analog signal, need to convert in, need to send to the plant, because the plant doesn't understand the other interfaces, other signals. So that's why again it need to be converted into the analog signals. So to convert the analog signals we need a digital to analog conversions. So here we are using the DACs, number of DACs are used. Why it is? Because when compared to the analog to digital computer, the DAC is very cheaper, so we can use a different DAC for different signals, and that will be sent to the plant. Okay, so the same thing which is given, the digital to the analog conversions is much simpler than the analog to digital. It can be provided one converter for one output. So the each DAC is connected to the data bus, and the appropriate channel is selected by putting the appropriate channel address on the computer address bus. So the DAC which is accessed on the latch holding and previous values sent to unit and the new value which will be sent, and then conversion time is typically from the 5 to 20 milliseconds, and typically the analog outputs are -5 to +5 and -10 to +10 volts, and current output of 0 to 20 milliamps. So the next one is real-time clock. So the real-time clock is nothing but an auxiliary device for control of computer system. It may or may not be a clock. In many systems it is a pulse generator with a controlled frequency. A common form of the clock is using a AC supply line to generate the pulses at the 50 times or 60 times per second. Using slightly complicated circuitry, higher pulse rate can be generated, the 100 pulses per second. The pulses are used to generate the interrupts and interrupt handling software that counts the interrupts, and hence it keeps timing. So the hardware timer which is used is more precise is required. Okay, so the fixed frequency pulse generator, usually it is on the crystal driven. The decrements the counter which when it reaches to 0 and generates an interrupt and reload the count value. The interrupt activates the real time clock software and the interval at which the timer generates an interrupt, and hence the precision of the clock is controlled by the count value loaded into the hardware timer. Okay, so the method whatever it is suggested above, which suffers from the disadvantages of the CPU spend larger proportions of the time, service time. So because of that the power is lost, the clock stops and restarting when the current values of the real time that has to be set again. So the real time clocks are now available where the clock and the date functions are carried out like a digital watch interrupt that can be generated at a certain frequency changed through the programming. It has a battery backup as well as. Okay, so the applications are in the batch processing, which provides the date and time in the printout etc., or an on-time computer system to provide the access to the several terminals using the processor known as the time, which is called slicing. Okay, so these are all about the interfacings of process related interfaces which is connected to the plant. So it may be an analog interface, it may be a digital interface, or it may be a pulse interface. So in this topic we have talked about the different types of interfacing which is connected to the plant. So what are the functions of that particular interfacing we have talked about. I think this video is very helpful for you, and these are the references. We'll see you in the next video. Thank you all.